Hi, folks. It's been a little while since I've actually used this utility, so hopefully this goes okay for me. I wanted to do an example problem here over waves on strings. This says that we have a 120 centimeter long 4-gram string that's oscillating in its n equals 3 mode with a frequency of 180 hertz and a maximum amplitude of 5 millimeters. So just to refresh us on where we were the last time we talked as a class, we um, we talked about strings that are fixed on both ends that then are oscillating in their different harmonics. It could be the first harmonic, second harmonic, third harmonic, fourth, so on and so forth. And I sketched out, um, what those various harmonics look like. And we also determined a formula for the allowed wavelengths of standing waves on strings and the allowed frequencies of standing waves on strings. Okay, so that's what this example problem deals with. So the first thing we're supposed to do is sketch the standing wave that's on the string for this n equals 3 mode. And then from there, we're supposed to determine the wavelength and the tension in the string. Okay, so there's our goals. All right, so we'll see if I can get my pen going here and yeah, and PowerPoint so that we can do this problem. Okay, so in part A, let's change the color there. We just want to sketch the string. So give it a couple of fixed ends there. Oh, all right. And then it says it's oscillating in its n equals 3 mode. So that means it's going to basically have 3 peaks, something like that. Okay. I don't know what happened to my other dot. All right. And to kind of maybe show that this thing is oscillating up and down, we can draw in something that looks like this. Okay. So those various peaks there are oscillating up and down, but the wave isn't moving back and forth left and right. So we see that we've got one, two, three antinodes there. So those are our high points. And then we've got, let's see, one, two, three, four nodes. There's supposed to be a four. I think there's a little debris on the screen or something. All right. So that's the answer for A. That's what our standing wave would look like. Now, let's see. It says here in our problem statement that this string is 120 centimeters long. 120 centimeters, that's 1.2 meters. So that's how long that string is. And so each one of these half cycles then, we've got 1, 2, 3 half cycles, and 1, 2, 3 antinodes. Each one of those three is going to take up some portion of that 1.2 meters. If we look, we've got 1.2 meters. And let's see, there's, 3 of those half cycles. That means that each of these half cycles is 0.4 meters long. Okay. All right. And, oh, and let's see if we start to think about things a little bit here. We've got 0.4 meters there, 0.4 meters there, and 0.4 meters here. And then if we look at, let's see, maybe a full cycle, which would be right there. We've got a full sine wave there. That distance would be twice 0.4 meters. This would be 0.8 meters. All right. And so that's the wavelength of our wave. Okay, this is part B. Okay. And then let's see, part C says we're supposed to calculate the tension in the string. Okay. And so for this, we're going to have to think of maybe a utility, a tool from an earlier chapter. But what I'm going to do is I'm going to try to give us a little bit of clean room here. Okay. we have figured out that the wavelength is 0.8 meters. Let's see, we are given that the frequency of these waves is 180 hertz. So that says 180. And then from this information, we can calculate the speed of the wave on the string. So V is equal to lambda F, 0.8 meters times 180 hertz. Looks like 144 meters per second. There we go. Okay. And now that we have that, we can think back to, let's see, like I said, prior information. This says the speed of a wave on a string is equal to the square root of the tension in the string divided by the string's linear mass density. Let's see, I can rearrange this equation a little bit by squaring both sides. And then I can go ahead and solve for tension, my force F there. Let's see, if I multiply both sides by M over L, I get force is equal to V squared times M over L, or tension is equal to V squared times M over L. And I've got, well, shoot. I hate it when it does stuff like that. There's a little, like I said, debris on the screen probably that causes some headaches when we're trying to write on it. 144 meters per second. All right, and then let's see, the mass of the string, it says it's 4 grams. Of course, we don't work in grams, we work in kilograms. We work in SI units, 0.004 kilograms. And then the length of the string is, let's see, 120 centimeters. Again, SI units, 1.2 meters. All right, and when we perform the calculation there, we get out that the tension here is 69.1 newtons. All right, and that is the answer for that. So again, this is just a little example problem of a wave on a string, strings fixed on both ends, and we're looking at the harmonic modes that this string would support. All right, and that finishes up our discussion of this chapter. There's a record button in here somewhere. No, no. Where is it? Oh, there it is. Okay, bye.